Alright, my name is Maggie Fowler and I will be talking about Lab 3. So in this lab, we calculated the distance dependence of a permanent dipole magnet and the off-axis magnetic field. And to do so, we used the magnetometer app. So the first thing we had to do was compensate for the Earth's magnetic field. So we had to align our phone to the Earth's magnetic north-south axis, which is where the x component of the magnetic field is 0. So in Atlanta, when the x component of the magnetic field is 0, the net magnetic field will be 49 microteslas. And when I first opened my phone and I was indoors and I found where the x component was equal to 0, my net magnetic field was 38 microteslas. So then I actually went outside and did the same thing and found where the x component was 0, and then my net magnetic field was 47 microteslas. So I did the experiment outside, and then you had to find the location of the magnetometer in your phone. So the first thing you had to do was you had your meter stick facing like east-west, and then you put your phone vertically on top of it, and you moved it up and down, and you found the location at which the x component of the magnetic field was at a max, and the y component was at a min. And then you put your piece of tape down, and you flipped your phone horizontal, and you moved it up and down again, and you found the location at which the absolute value of the y component was at a max, and the x component was at a min. And now you put your piece of tape down again, and where the two pieces of tape cross is where your magnetometer chip is in your phone. And then from here, you had to find the distance r from the bar magnet for 5 different values of the x component of the magnetic field. So you just moved your phone from right to left with the magnetometer chip lined up with your bar magnet, and for each of the 5 different x components of the magnetic field, you solved for r 3 times so that you could average it out and try to account for some human error. And then in terms of physics principles, we used the Biot-Savart law and the equation for the magnetic field of a dipole. And then like I mentioned a second ago, there was some human error in taking measurements. And then in terms of observations, we had to talk about which of the statements described what we observed. And I said that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And then when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And then here's my data and measurements. So like I mentioned earlier, we had 5 different x components of the magnetic field, and for each one, we found the distance r 3 times, and then we averaged the r and we averaged the x component of the magnetic field, and then we took the ln of r and the ln of the x component of the magnetic field. And the reason we took the ln of both of those is so that we could plot this graph right here. So we have this equation that the magnitude of the magnetic field due to the bar magnet equals k times r to the n. And so when you take the ln of both sides, you get that ln of the magnetic field due to the bar magnet equals ln k plus n times ln r. So in this situation right here, negative 2.6092 is our n, and negative 13.378 is ln k. So from there, you can solve for k, and you can solve for mu, because we know we're talking about an on-axis dipole. So k equals mu naught over 4 pi times 2 mu. So by knowing k, we can solve for mu. And then we found the off-axis magnetic field. So what we did here was we moved our phone to the right of the bar magnet a distance d perp such that the magnitude of the magnetic field was 100 microteslas, and then we moved it up that same distance d perp. So now it was a distance d from the bar magnet, and then we did this 3 times for 3 different d perps, and each time we entered our components of the magnetic field, and then we accounted for the Earth's y component of the magnetic field, and we solved for the b net. So here's my coding. We didn't do a ton for this lab. We put in our mu that we calculated earlier. We put in a little function to create the magnetic field. We messed with the b scale and the distance a tiny bit, and then we added 6 observation locations, 2 on axis and 4 perpendicular, and then we made 2 arrows that represent the magnetic field on axis and 4 arrows that represent the magnetic field perpendicular to the axis. And then over here we have our arrow that's off axis 45 degrees, and then we did put in our d perp here that we just calculated. And then this is their computational model. You'll notice the orange arrows are the magnetic field on axis, the blue arrows are the magnetic field or perpendicular, and they're facing opposite directions. And then the magenta one, this is the magnetic field 45 degrees off axis, and it's kind of hard to tell, but it's going over and up, so to the right and up. And then for the final questions, so if we hadn't oriented our experiment to compensate for magnetic north, then the Earth's magnetic field would also have affected our measurements, so then we wouldn't be sure what the magnetic field was due solely to the bar magnet. So our values for N, K, and mu would not be accurate. And then if you were to stick two identical magnets together, I believe the magnetic fields that we'd measure would be in the same direction but would have a larger magnitude.